Hello. I think we will not wait for others because only six students are here. So I'm not sure your performance in your in-class test. I didn't start to mark your answer scripts yet. So I think I will not send you the solution of the test paper. However, so me later today, in fact, we will have a revision and let's work on our test paper together. So then it's kind of a revision on what we have learned in the past few weeks. In fact, firstly, let's see what we have learned in the past few weeks. Firstly, we learned the four laws of thermodynamics, including the zeroth law, first law, second law, and a third law of engineering thermodynamics. Then we understand for our subject, we want to study the relationship between work and heat. Okay, work and heat. Then we know we have to understand the properties of our working fluid in our system. Okay, so for any device or heat engines, so we have the properties, their properties. So we know according to first law, for the first law is energy conservation. We understand energy cannot be created or destroyed. There is only energy transformation from one form to the other. And then, in fact, for engineering thermodynamics, we mainly have interest in work and heat and their relationship. So we know that according to second law of thermodynamics, we know all thermodynamic process has its direction and energy has their values. So therefore, if we want to, we know heat transfer usually, and also thermal energy is heat is special. And we know that for heat transfer is always from high temperature to low temperature. And therefore, if we want to convert heat, okay, we convert heat to work, we need a forward heat engine. Okay, we need a forward heat engine. And we want to extract heat, okay, extract heat from low temperature, okay, from a low temperature environment. Then we need reversed heat engine. So therefore, we have learned forward heat engine and the reversed heat engine. So for first heat engine, we understand that there's a thermal efficiency. There is a Carnot cycle, Rankine cycle, and improved Rankine cycle. For reversed heat engine, so the application including refrigerator and heat pump. So we understand how to examine the performance is the COP. Okay, we know that reverse heat engines can be on reversed Carnot cycle and ideal vapor compression refrigeration cycle. And next week, we will learn their actual cycle. Okay, so now let's work on our test paper together. Okay, so in fact, for the property, we have newly learned entropy and enthalpy. Okay, entropy and enthalpy. So the first question is on entropy, because entropy is derived from the second law of thermodynamics. We want to examine the thermal equilibrium of a system. So for an isolated system, it's always towards increase. Okay, I'm not sure if the solution is correct or not, incorrect. Okay, let's work on it together, because this is just, I prepare for your exam, then I work on them by myself. Okay, so the first question, the entropy of working fluid of ideal Carnot cycle. So for ideal Carnot cycle, we know it's reversible. Okay? During the isothermal heat rejection process, okay? We know we know the difference. We know it's the change of okay, for reversible process. Okay, the change of entropy. In fact, there is a proportional relationship to the heat flow. So therefore, it's decreased because heat rejection process is losing. There's a heat rejection process. There's a decrease of the entropy. So therefore, for the first question, okay, our solution is decrease. Okay, for second, the specific enthalpy of vaporization. So this is regarding the properties. Okay, then we remember. So for there is a on the pressure enthalpy diagram. So there is a saturation line. So with the increase of the pressure, okay, so then the horizontal line is shorter and shorter, which means this is means specified a specific enthalpy of vaporization. 10 bar is smaller, okay, with the increase of the pressure. So the horizontal line gets shorter and shorter. So then it's smaller. Then what about the third question? This I think I have asked you work on it through your assignment. So I think next time we will work on our assignment number 1 together. So for this question, because I asked my PhD students helped in marking the assignment. And so for the compression process, so if with the given, so for the given, so with the given starting state 1, then we need to compress it to compressor, small pressure. Oh, I see. Compress it. Let me see. With the given pressure to compress it. Okay. Let's. Okay, state 1 and 2. Okay, compress it. Okay, to state 2. So let's see. Okay, maybe this answer is wrong. Okay, this is compression. So last time I think I'm working on expansion process. And then for the process with different value, okay, this is 1 with 2. So let me see. If with 0, okay, 0 is here, with 1 0 here. So this is with higher, larger 0, and then 1 or 2. Then maybe this is 1 with is isothermal process, and for this is so therefore we can see the required work input of process 1. Process 1, this is process 1. This is process 1. This is process 2. So we can see the shaded area is larger. Okay, is larger. Okay, so it's A. The solution is A. Okay, so then question number 4 is the calculation of the isothermal efficiency. So what we have to be careful is here is this is the high temperature, this is the low condensation temperature, and we have to use absolute temperature. Okay, then this solution is A. So this is if for the heat pump and the refrigerator, then it's reversed heat engine. So this is we can see for this one is expected for heating. Okay, expected for heating. Okay. So therefore, the COP has to be for the heat pump, okay, for heating, for heating. So it will be equal to, I think here is okay. So this is the solution. Let me know if you think my solution is wrong, because I'm working on the solution by myself yesterday, also just within 10 minutes. And then this is for also regarding to the properties. Okay, the properties, we need calculate the dryness fraction. Okay, we can refer our tables. Then for question number 7, this is first law of thermodynamic application. Okay, I think the calculation is positive, then it means their absorption. Okay, then we are working correct or wrong. Rankine cycle is practical because it's high, it's lower. Okay, in fact, it has lower thermal efficiency, so it's false. And then for 9, entropy is surrounding, so will only increase. Okay, increase, will not decrease, is because it's for isolated system. Okay, then for isentropic expansion process produce the maximum. Okay, this shall be maximum power output. And the entropy of working fluid ideal Carnot cycle will decrease during the absorber heat absorption. Is wrong. Okay, this is will increase. And so for 12, the two-window air conditioners operate on the reverse Carnot cycle. The one operates have lower. Okay, so that means a hotter outdoor environment. It means higher condensation temperature. Lower COP. And this is for isochronic with a constant volume. Then, as I have mentioned, if volume no change of volume, then there is no work. And during a reversible heat rejection process, the entropy will decrease. Yes, it's true. It's similar to our first question. So, do you have any question on these 14 multiple choice questions and their solutions? Okay, I'll leave 1 minute, see if you have any question. If you have no question, then we will have a look at the short question solutions. Okay, for question 12. So for question 12, is for the reverse heat engine. And we know generally, we remember the COP calculation. Okay, COP. If for the reverse Carnot cycle, okay, here is the low temperature, right? So here is the high temperature minus the lower temperature. So now let's see what will affect the results, the calculation results. So if we want to increase COP, okay, then we need, increase the low temperature. The low temperature is evaporating temperature, and we shall lower the condensation temperature, the high temperature. So for this case, is the hotter outdoor environment means the high temperature is higher. Okay? If it's higher, so we can see the COP value will decrease. So that's the reason even for our home air conditioner, we should place our outdoor environment in a shadow place or with good ventilation. Otherwise, surrounding air temperature is too hot, then the performance of our air conditioner will be worse. Do you think you understand, Ji Chen, this question? Okay, thank you. Okay, now let's work on the short questions. So for short questions, the first one, I think is a closed system. Okay, it's closed system. And therefore, for closed system, if we apply the first law equation, then so here please remember it's always final minus initial. Okay, then if the results with is negative or with a minus, then it means it's heat rejection. Okay, or you can you tell me so it's a heat rejection. Okay, for the system. Then it's similar to the multiple choice questions is the thermal efficiency of a forward heat engine. Okay, so please be careful is here we have to use absolute temperature. Absolute temperature. Okay, so this is for question number 2. So for question number 3, and is a refrigerator. So we are using here, this is the low temperature. Okay, the low temperature, absolute temperature, and this is the difference. So after calculation, we calculate. So in fact, for in-class tests, I try to examine the conceptual equations and concept. So your understanding. Then for this question is similar to the multiple choice question, but I provide you the heat flow. Okay, so then we understand that for this heat pump, okay, it provides our heat. This is for heating. We expect the heating. Okay, so here is 600 kilojoule. Okay, and then we find is extract heat. Kilojoule. Then, according to first law, we know that in fact for the work, okay, for the work, it shall be 150 kilojoule. Okay, so therefore the COP of the heat pump for heating shall be the expected output is the heat over the required input is the work. Okay, then we can calculate the results, the COP, okay, as a 4. And for the question number 5, I'm not sure. For this question, I think you need to clearly indicate how you construct the question. Okay, I will deduct your marks if you didn't follow my requirements. For example, here you have to provide me is on the pressure line. Okay, this is for the evaporator pressure. Okay, that all they are on the pressure lines. On the evaporator line, you cannot just draw randomly. Okay, you have to draw based on my given conditions. So this the shaded area is the cooling effect. Okay, for the COP calculation, firstly we need to calculate by applying the first law of thermodynamics to calculate the cooling effect. Okay, the cooling effect over the required input is the COP. So, do you have any question? I leave 1 minute, see if you have any question. Okay, if you have no question, then I will leave all later. Okay, then there are two comprehensive questions. In fact, this question is similar to your assignment. It's the same. I just I provide you solution here. However, I found many of you just maybe just copy from others. Okay, you didn't provide me the deriving process and why you get this equation. Okay, so I think half. If you didn't clearly provide me the deriving process, I think at least 1/3 or half marks will be deducted because it's open book exam. You can easily copy from others. Because even for assignment, I found some of you don't really understand the question. Just copy the solutions, the answer from others. Okay, so therefore my students, I think the marking grading is very strict. And for the question is two reversible forward heat engines. They operate in series between a heat source and a lower temperature reservoir. So if the engines, two engines have equal efficiencies and the first engine receives 600 kilojoule heat, we are asked to calculate the maximum energy efficiency of the engines. Okay, in fact, let's look the two heat engine. This is the first heat engine, the second heat engine. So for the first heat engine, the temperature is 600 degree. 600. Okay. Okay. Here is 20 degrees Celsius. So then we can see, in fact, for the first heat engine, this is the high temperature thermal reservoir. Okay, then its fanny is here. So we can see here is the low temperature thermal reservoir for first heat engine, but it's the high temperature thermal reservoir for the second heat engine. Okay, if you can draw this diagram correctly, I think you understand the meaning of this question. Okay, if you didn't provide me this schematics, okay, and this drawing, maybe some I don't think you understand this question. Maybe you just copy from others. And then, so we assume there is a temperature here. Okay, it's temperature 2. So this temperature is the low temperature of the thermal reservoir for the first engine, but it's the high temperature thermal temperature of the high temperature thermal reservoir. Okay, there is a temperature 1, 2, 3. However, so the intermediate temperature 2 is special because it's the low temperature of the first heat engine, but it's the high temperature of the second heat engine. So because for the given question, they have the same equal efficiencies. So therefore, for the engines, their thermal efficiencies, okay, are same. So we can say for the first heat engine, this is the low temperature, but becomes the high temperature of the thermal second heat engine. Calculate, in fact, the second, the temperature 2. Okay, this is the temperature 2. And then we calculate the for each engines, their thermal efficiency is the following Carnot cycle. Okay, on the Carnot cycle. So this is their efficiency. And then accordingly, we can calculate the work output of first heat engine and the second heat engine. Okay, we are using the heat flow, okay, to calculate the work. So I'm sorry. I think you need to watch the recording. So after tutorial session, because I will not share with you the solution, the standard solution of in-class test, because every year sometimes there are some same questions will be examined. So I will not share with you. And then we can calculate. So if there's two heat engines connected in series, then their total work. So each heat engine has work output. So if the total work output is, we get the total. So we can calculate the value. Okay. So do you have any question on this? On this question, on the forward heat engines connected in series. Okay, if no question, let's work on the last question together. Last question is forward heat engine again. So it's on a steam plant. So we can see question 7 is we know the rated power output is 100 megawatt steam plant operates. So this value is rated work output. Operates on the Rankine cycle, but with the turbine isentropic efficiency. So as I have mentioned, so there's an improved actual Rankine cycle. They can be irreversible. So this is mentioned. So expansion process is irreversible. The steam enters the turbine at 7 megapascal and with temperature. So we check it. It is started to the condenser. We plot the on the temperature entropy diagram and determine the thermal efficiency with the maximum 1. So in fact, for this question, firstly we need to draw the constant pressure line. Okay, the constant pressure line. This is constant pressure line, and then we got the saturation temperature. We compared it. Then we found state 2 is superheated. Okay, we got state 2. Then we also get state 1 or state 4 because this is wet saturated. This is a ideal isentropic process, okay, compression process. Then, however, here this is if it's an isentropic process. However, for the actual one is with isentropic efficiency is irreversible. Okay, according to the definition, we have increased the enthalpy. Okay, actual enthalpy is larger, entropy larger than for isentropic reversible process. So therefore, state 3 is here. If you are here or here, I will also think it's okay. Just you have to know you have used dashed line, and then there's increase of entropy compared with the ideal isentropic process. Okay, then we are asked to calculate the efficiencies. And based on the isentropic efficiency calculation, we can get the specific enthalpy, and we calculate the cycle thermal efficiency. Then accordingly, it's the same. Okay, is work. We neglect the pump work input. So then this is cooling effect. Okay. We can calculate the efficiency is 32.3. However, for the ideal one, we know for 7 megapascal, we got the saturation temperature. Okay, this is the saturation temperature. Then we can calculate the maximum possible thermal efficiency on the on the Carnot cycle. So we can calculate it's 40.4%. Then we know, in fact, the actual efficiency, thermal efficiency, is smaller than the maximum one. The maximum one is on the Carnot cycle. Okay, so this is for our in-class test. And so for next tutorial, maybe we also spend some time on our assignment number 1. Then we still have, I think, 5 to 6 minutes. See if you have any question on what we have, what's the solution for our in-class test. And also we have just simple, quick revision. Okay, what we have learned in the past few weeks. Okay, I think I will stop recording. I'm sorry, I will not provide you the solution, this file with you, because every year, in-class test, there are some similar questions, okay, from year to year. So I will not share with you this file. So just follow our tutorial and then if you need, you can have a screen capture, okay? But not I will not share the file with you, the file. Okay, thank you. I stop recording. See, the following few minutes is for question and answer.